In lesson 1.2, we're going to be introduced to a new unit of angle measurement called radians. Recall that in lesson 1.1, we talked about angles on the coordinate plane, and we said that the standard position of an angle had its vertex on the origin, with the initial side fixed to the x-axis, and the terminal side somewhere on the plane. A positive angle, or positive theta, meant counterclockwise rotation. Negative theta implied clockwise rotation. And in lesson 1.1, we always measured our angles in degrees. But a question you should ask yourself is, why are angles measured in degrees? Okay, where did the degrees come from? And we say 360 degrees is one full rotation. But why? Well, if you go back to the ancient Babylonians, they studied the stars and noticed that about 360 days later, the stars ended up in the same relative position of the sky. We know that there are 365 about days in a year, so 360 there measured is about the time that a year takes. So we could say there's approximately 360 days in a year, which is one rotation of the Earth about the sun. And if we're thinking about very fundamental things to humans and civilization, you've got your Earth and you're scooting on around the sun, you might choose to define rotation based on this really important fact. And they did their best to measure, and they said 360 seemed to be right. Additionally, the Babylonians did their math in base 60. And bear in mind, all of these facts are like quote-unquote facts. They're Miller facts, so go verify them on your own. But I think they're right. So anywho, they did their math in base 60. Now, we do our math in base 10. And what does that mean? It means we basically have 10 or 9 symbols. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 to represent quantities. And then when we fill up those symbols, when we get to 9, we say, well, we don't have a new symbol for 10, like, I don't know, 10 could be this, right? Or something like that. And then 11 could be this, and then 12 could be, like, we could keep making symbols, but instead we say, oh, when we get to 10, we just bump it to the next column. So then we go 0 in our ones, and we add a 1 to the next column. And then you can go keep counting, 11, 12, right? And so now we fill this next column, the tens column, and keep counting in the ones column. Base 60, that means they had 60, or maybe 59, I don't know, symbols for numbers. So they could keep going. They would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then, well, 10 wouldn't be written like that. Maybe they use a star for 10, and then a crescent moon for 11, and then a box for 12. I have no idea. Go look it up. But the idea is they had 60 symbols, so they could keep writing in the single digits column, and then eventually they'd get to the next column and they'd have to write, okay, now we have 1, 1, but that would mean 61, right? Because they filled up in base 60, 1, 1 is 61. So that's pretty interesting. So base 60, and you'll notice that 60 times 6 equals 360. So working in base 60, 360 seems pretty natural. And then there's one more interesting fact about 360. 360 is a pretty, I want to use the word amicable number for doing math by hand. Because it has many, many integer factors. We can have 1 times 360, 2 times 180, 3 by 120, 4 times 90, 5 times 72, 6 times 60. So already we're divisible by 1 through 6. 7 sadly does not work, but we can do 8 times 45. We can do 9 times 40, 10 by 36. Can do 12 by 30. Sadly, 11 doesn't work. We have 15 times 24 and 18 times 20. So look at all these integer factors. Whoa. integer factors, right? We have lots of things that we can do our math with and have subdivisions of 360. So we can divide up our one full rotation, 360 degrees. It's pretty easily to chop that into fourths or into eighths or into tenths. Like, we can subdivide and get really nice angles to work with. So for all these reasons, 360 degrees is pretty good, and it's stuck around. But sometimes there's reasons that we might want different units of measurement, right? In theory, we could have picked anything. Degrees are arbitrary. The fundamental sort of unit or measure of an angle is one full turn. And that's sort of the fundamental unit of angles, or rotation, if we think about it in that sense, is one full turn. Like, if we're facing this way and we rotate one full turn, we're back to facing the exact same way. Now, we can call that full turn. We can call it 360 term. We can call it 360 degrees if we want. We could call it 100 degrees, right? And define it differently and say, oh, 100's a nice number that we like to deal with because we're in base 10. And call it 100 degrees and divide it up like that. You could use hours. You could call it 12 hours and say, well, 1 hour corresponds to 1/12 of a turn. You could do minutes. You could divide it into 60 minutes and say minutes can correspond to a 60th of a turn. Let's use that for our angle. If I wanted, I could call it 8 Miller units, right? Instead of degrees, we could do Miller units. And so if I have one full rotation and I say, well, 1 Miller unit is 1/8. So here we go. There's 1 Miller unit. And then 2 Miller units is a fourth. And then 3/8. And then 4/8, 5/8, right? I could divide it up like that if I wanted. But we're going to learn one that's actually used in the real world. A new way to measure angles. A new, useful way to measure angles. And that is called radians. So why are we going to use radians? It's going to, and you might get this clue from the word radian, right? It directly relates an angle measure to the radius of a circle. Thinking about a circle as representing one full rotation, circle has some radius r, and a radian is going to relate that angle measure directly to that radius. It's this sort of fundamental relationship, right? A circle is sort of, in a sense, defined by its radius. So if we were to want to measure the circle based on that radius, we can use radians. Another thing that's going to be nice is because we're basing it off radius is like a length. So we're going to be more easily able to work between linear lengths and angles. So if you're measuring in degrees or hours, minutes, Miller units, whatever, you kind of have to convert between lengths and do all these different proportions, which aren't that hard, but it's a little extra. But if you measure in radians, you're going to be able to go directly between the radius and the angle. So linear lengths and angle measures without having to change units. And I'll tell you what they are in a second, I promise. Okay. And then the last thing is calculus. Okay, so doing radians and doing a bunch of calculus, radians just end up being nicer. So that one's not going to come into play until you get to calculus. So you just have to have good faith that this work that you do in radians will pay off in calculus because A, the calculus community, the math community, does all their math in radians. And B, it's just better to do it that way. Otherwise, you have all these weird units, and who needs that? Okay, so if we said the fundamental unit of an angle is one full rotation or one full turn, Well, then the question you should ask yourself is, how many radians is one full turn? Okay, so if I have this unit called radians, how many radians is going to be one full turn? And what you should do is think about the circumference of a circle. The circumference of a circle is equal to 2 times pi times the radius. So it turns out that 2 pi radians is one full turn. Okay, and in a sense, 2 pi radians will end up being equivalent to 360 degrees. Both represent one full turn, or 8 Miller units, or 12 hours, or whatever. Okay, but still I haven't really shown you what a radian is. So a more technical definition of a radian is 2. So a radian. This is going to be a Miller definition. Google it if you want a better one. But the way I think of a radian is take the radius of the circle and wrap it around the circumference. Okay, so if I have my circle here that represents one full rotation, if I have a radius, right, length r, if I take that radius, right, length r, and if I wrap it around this circle like such, and so here it goes, and I get some distance, r, right, and I'm able to cover a radius length on the circle, that is 1 radian. So the measure of the arc that it covers is 1 radian. So I sort of visualize it as take the radius, wrap it onto the circle, however far that radius makes it is 1 radian. Okay, so if I can complete this little angle here and put a theta, I've got 1 radian. Now, we said there were 2 pi radians makes 1 full turn. Okay, well, how much is 2 pi? 2 times pi is about 3.14, right? So if I multiply these two, there are about 6.28-ish radians in 1 full turn. Okay, so that means if I have some circle, yeah, very nice circle, and if I have my radius, call this r, and I start wrapping that radius around, so let's go, I maybe get to here, oop, nope, I would get to here-ish, so there's 1r, then let's do color changing, then I'll do 2r, that's another radius, here I get 3r's, 4r's, might have to cheat a little bit, 5r's, yeah, I didn't do a great job, call that 6r's, and then a little bit more, and then the last part here is about 0.3r's, right? So the idea is there's that many radiuses wrapped around the circle. And in total, we have r plus r plus r plus r plus r, 1, 2, 3, 4, 5, 6, and then about 0.3r. So then we get about 6.3 radiuses, right? Wrapped around the circle, aka exactly 2 pi. Wrapping around the circle. So that's the idea of what a radius is. So if I said that an angle equals 1 radian, guess what? There it is. That's theta of 1 radian. It's just how far that angle makes it. If I said that an angle was, let's do blue, keep it consistent. I said theta is 2 radians. It's describing the angle here. It's saying we take 2 radii, wrap around the circle, and that's how far we make it. And if I said maybe that theta was half a radian, 1/2 a radian, well, then that would mean I get halfway there. And there's my theta of 1/2 of a radian. And radians are the default, like they're kind of unitless. So if I were to just say theta equals 1/2, that is talking about radian. So I don't even have to write this radian. I can just write theta equals 1/2, and like this is in radians. It's kind of interesting. So, okay, that is all pretty nice. And that's what a radian is. Now, how do we kind of conceptualize and deal with these radians? Let's see. Let's actually make that another video. Okay, so hope you enjoyed this. Hope that helps explain what a radian is, and I'll show you how to work with them in the next video. Thanks for watching.